Hello, let's make a top-down city-based car crime game.
As you may have seen in the thumbnail, this is a big project, and to all the newcomers to the channel, welcome by the way, that means we'll be splitting this over several episodes. And I try to start each episode by showing what we're aiming for. And as you can see, we have a car here, and we're driving around a city. There's no collision detection yet, so I'm only really showing what we'll be getting done in this particular episode. Now when I do a big project, I like to use things that I've shown in previous videos and build upon them and show how it all comes together. And here we can see the city is using the 3D engine, but I'm also using the Pixel game engine. At the moment, all the graphics are quite simple and are really just placeholders whilst we develop the game. I think this is quite an important strategy, just to make sure that first of all you can get it to work and then make it work well. And when I say a top-down city, I mean a top-down city. So we'll be looking at how we're handling the 3D graphics, we'll be looking at things like collision detection, we'll of course be adding non-player units such as police cars and possibly pedestrians, and we'll need some sort of mission-based system. So there's quite a lot to get on with. But I quite like the aesthetic already. I've spent lots of time developing this city and driving around it. It's quite fun. Now when we're working with a game that has a large amount of rich detail such as this, it's quite important that we also develop the tools to help us develop the game. So in this video we'll show some very basic city editing tools. In fact, I can show you some now. Using the mouse cursor, I can place it anywhere in the scene and place additional roads. And you'll see that the roads automatically align themselves with the correct junctions. And I can remove the roads as well. I can also place buildings, and I can place buildings of different height. I can grow the buildings up, and I can grow them back down. And as a little bit of novel interaction, I'm using the car to control the camera. But editing a city like this might take some time doing it tile by tile, so I've also implemented the ability to select tiles in the scene and apply the same transformation to all the tiles simultaneously. And the selection works at any zoom level. One of the principles I try to adopt when I'm developing a game is that the game and the game editors should try and use the same engine. And the primary reason for this is that you can edit the game as necessary whilst you're playing it, so you can fine-tune it quite easily. I'll just show a little bit more road building as we can connect these two roads together.
As you can see right now, the game is in a very basic form. The graphics look a little bit repetitive and a little bit square. And that's simply because they're placeholders. Let's make it work before we make it work well. We'll have to keep remembering this mantra. And what is especially important before taking on any larger project is that you have a plan. So let's get started.
Clearly this game is inspired by the classic Grand Theft Auto series. But I don't intend to clone it completely. I'm going to be making a much more cut down, simpler version. So what are the features that I'm aiming for in this game? Well, the first thing I want is a large city. And I want the ability to choose and drive cars. You need cars to get from A to B, which implies some sort of mission-based activities. The city would be a bit boring if it was empty, so I'm going to need some traffic in there as well. So I'm going to have some other cars. And as with the classic Grand Theft Auto, the player could literally steal a car that they saw driving around. Typically the missions will involve with you being chased by a police force. So I think a particular game dynamic is to evade capture. In games I personally like collecting things, so I'll probably have some pickups in there as well. And because the city is quite large, we're probably going to need a few things to help us. We might need some navigation aids, like a GPS system perhaps. We're going to need some editing tools. For the different cars, they're probably going to have unique properties, such as speed and handling, or resilience to damage if you crash them into things. And that's quite an important thing, because if we're driving around, we're going to need some collision detection. I don't want the missions to just be to go from random location A to random location B. It would be more fun if they tell a bit of a story. So we want the missions to be scriptable. And this has already got me thinking, because if we're going to have assets with variable properties, and we're going to have gameplay with variable properties, perhaps just maybe we want these to be modifiable. So we might want to think about using an external scripting language to handle this. Now, traffic, and in some ways evading capture, are going to need a degree of pathfinding, perhaps. Potentially some sort of AI. Realistically, pickups are the easy ones in this.
Now, the nature of a big project is it's a big project. It's quite large, it's got a lot of elements to it, and as such, typically during a big project I don't go into as much detail on all of the precise elements, and I might skip over some of the code that we're going to write, which means these videos tend to move at a little faster pace than my normal videos.
I'm going to start with a blank Visual Studio project, and to this project I've added the OLC Pixel game engine and a blank source file for videoccc1.cpp in this instance. The first thing I'm going to do is take the template from the header file and paste it into the source file. This is just a very quick and easy way to get set up. And what I will add at this point is, please don't forget to define OLC PGE application before you include the game engine. I'll just quickly modify the template to suit our needs. And I'll remove the things that we don't need in OnUserCreate and OnUserUpdate. If you're new to Pixel Game Engine, OnUserCreate is a place that only gets called once, so you can use this to load your resources, and OnUserUpdate is called every frame. I'm going to create a Pixel Game Engine which is 768 pixels wide by 480 pixels high. So it's a widescreen application, so I'm going to reduce the pixel size because it's quite a high resolution too, so I want it to fit on my monitor. I want to keep many aspects of the game very, very simple indeed. So I'm going to restrict my city to really just being a two-dimensional array. Where each cell in the array represents something different. For example, I'm going to want to know if a cell contains road or not, so we'll have a flag that indicates if it's a road. I think it might be quite useful later on, when we're dealing with navigation, to know that roads are distinct. If the cell isn't a road, then presumably it contains some sort of scenery. And for now, I'm going to represent that scenery using a single integer. For example, if the scenery integer is 0, then it's just flat, so we'll draw some grass. If the integer is less than 0, then for now the cell's simply not going to exist. But in a future video I'm going to want that to be water, and this gives me a third option for anything that is greater than 0. And I'm going to assume that any value greater than 0 is going to be a building, and that the value indicates how many stories that building has. So if it's a 1, then we have a single story. If it's a 2, then we'll have 2 stories. So there's the first one, and there'll be a second on top. So in my cell structure so far, that means I've got something that indicates road, which is probably going to be a boolean, and I've got an integer I'm going to call height. That's enough to get us started. Right now I'm making no attempt to optimize any of this at all, but I'm going to need some geometry for my 3D engine to render. I'm going to need several meshes. So the first mesh is just going to be a simple flat quad. 2 triangles. And I'm going to use this quad for rendering roads, grass, and the roofs of the buildings. Basically anything that's flat when looked down from above. The second type of mesh I'm going to use are sort of the outer walls. So if we're looking at this, we've got a southern direction here. We've got a quad that makes the southern direction. But in the same mesh, I'm also going to attach the other sides as well. That'll be our westerly direction, northerly, and easterly. I'm going to keep that as one single mesh. I'm also going to keep all of my coordinate systems in unit values. So our quad is a 1 by 1 unit quad, and our outer walls are going to be a 1 by 1 by 1. Not a cube, because I've not got a top or a bottom. However, whenever I'm working with 3D engines, I also want to include a cube somewhere because it's a good way of testing that you've got everything set up correctly. I've created some very simple placeholder assets too, and you'll notice that these are also based on a single cell size, particularly for the roads and grass. The top-down stuff is indeed square. The sides of the buildings here aren't, but laying out the texture in this way has revealed what kind of junctions I need. So I've got a north, south, east and west T-junction. I've got horizontal and vertical road segments, I've got 4 corners, and in the middle I've got a crossroads. So I've covered all of the types of road I want to have. This does imply a single constraint though, and that is that my roads must always be loops. Not only does this make the production of the graphics simpler, it's also going to help later on when we're dealing with the artificial intelligence and non-player vehicles. Because I've got a feeling things like dead ends might cause us a problem there. Because I'm using the Pixel Game Engine, I can export all of this as a PNG file.
When I first created the Pixel Game Engine, one of the things I wanted to use was extensions. This is encapsulated code that serves a particular purpose. We've already seen the Graphics 2D extension in the Affine Transforms video. Well, for this series, I've also created a Graphics 3D Pixel Game Engine extension, and it uses exactly the same code that I've used in the Code It Yourself 3D Engine series. But I've made a slight change to the structure just to make it a bit easier to use.
I'm going to include the extension at the top of our source file. Now, admittedly, this extension is quite a large file, and that's because there was a lot of code for the 3D Engine series, but please be assured it is exactly the same. We've got our Vector 2D and Vector 3D types, we're still using triangles, we're still using matrices, and we're still using meshes. I've encapsulated all of the maths routines that we developed in a subclass called Math.
I've still not got around to doing operator overloading just yet.
And so it's in here that I've got my matrix and vector operations. I've also got the clipping algorithms that we created. And if you are so inclined, you can compare the code in here to the code created for the Graphics Engine series, and you'll see it's exactly the same. However, to keep things neat and tidy in our source code, I've introduced the concept of a rendering pipeline. And this imitates the technique used by graphics cards from quite a while ago, certainly before we had shaders and shader model based GPUs. The idea is that you submit geometry, let's put some geometry here, some triangles, you submit that to the pipeline, and the pipeline will do things in a fixed order. So the first thing it might want to do is transform the geometry. So if you remember, that might take in, for example, the world matrix. It might take in something like a view matrix too. And why not? It may also take in the projection matrix. Once the geometry has been transformed, it may go on to do some lighting. Now these might not be in the precise order that we end up doing things. It may go on to do some culling or clipping, and finally it will raster the transformed lit, clipped and textured triangles to the screen. Pipelining in this way does reduce the flexibility of what you can do, but it really simplifies using the 3D engine. And so I think it's worth showing this first to just simply put a rotating cube on the screen, very quickly. I'm going to represent my cube using a mesh. So we're in the OLC namespace, then the Graphics 3D namespace, we're going to take a mesh. I'm going to call it Mesh Cube. And in the onUserCreate function, I'm going to define what that cube is, and I'm literally copying and pasting the coordinates that we used in the 3D Engine series. You can see it's exactly the same. Alongside my mesh, I'm also going to need a rendering pipeline instance. So again, we dip into the GFX 3D namespace, and I'm going to create an object of type pipeline. I'm going to call it pipe render. And I could have several different pipelines all configured differently for different rendering operations. But right now, I only need the one. In its current form, the 3D extension does require a little bit of initialization. I'm going to do this in onUserCreate. And all I need to do is simply call the configure display function. This sets up some internal buffers to handle the depth. I'll also use onUserCreate to set up some of the more static properties of the rendering pipeline, specifically the projection parameters. So we want a field of view, which is in degrees. I'm going to set that to 90 degrees. I want the aspect ratio, and these parameters will look exactly the same as they did in the 3D Engine series. Don't forget to cast that to a float. We need the near plane distance, the far plane distance, And then I'm going to add an additional 4 properties, and these are the viewport. So if you remember, we did quite a bit of transformation after we did the projection transformation in the previous series, and that was to scale it to the screen. So I'm going to define the screen as being a top left 0, 0, and bottom right, well, it's going to be the full screen, so we'll borrow screen width and screen height again. Typically, the projection information isn't going to change in this application. Of course, if you need something that changes per frame, you just have to set this up per frame. With any 3D scene, we're also going to need some sort of camera. So I'm going to add in 3 vector 3Ds here to define what the camera is. So we've got our up direction, our I direction, which is where the camera is in world space, and the direction the camera is looking in. So let's have a go at doing some rendering. In OnUser Update, the first thing I want to do is clear the screen to black. Now if you remember, the camera matrix doesn't take a look at direction vector, it takes the point the player is looking at, and we can get that point by simply adding the direction vector to the I vector. So I'm going to do that here. Create a vector called lookTarget, and I'm calling the vec_add function to add our look direction to our I point. And this will give us a point in 3D space so our camera matrix can be assembled. And we don't need to do that manually anymore, we can let the pipeline handle that for us. So I'm going to tell the pipeline to set its camera up using our eye location, the looking target, and the up vector. Now as you know by now, I like to test these things with a rotating cube, so we need to come up with the world transform for the cube. I'll do this the long way round. I'll create a matrix called mat_rotate_x, and we'll call from our maths library GFX3D math. Yeah, it gets a little bit wordy, I appreciate that, but at least it's clear. Mat make rotation, in this case the x-axis, and we want to specify an angle in radians. I'll create a variable floating point called f theta. I also want to rotate in the z-axis, so I'll copy that line and change this over to z. But I want to rotate at a different speed, so I'm going to change our f theta. So now I want to create a transform for the cube. We'll call this map world to stay with convention, and we're going to multiply the 2 rotation matrices together. Rotate x and mat rotate z. So we've now configured our pipeline with a projection transform, we've configured it with a view transform. The final thing to do is to configure it with the world transform for this object. Now it's time to draw the geometry. So I take our pipeline, I'm going to call the render function, which takes the vector of triangles associated with our mesh. So it was mesh cube dot tries. But this is where things get a little bit different from the series. We've got several different ways of rendering things. In this instance, I just want to render the wireframe. So I'm going to specify the render wire flag. And before we test to see if this works, we need to change our f theta value per frame. I'm just going to do that by accumulating f elapsed time. So let's take a look. And there we can see, it's a bit small because our camera is far away, but we've certainly got a rotating cube in the middle of our viewport, i.e. the pixel space screen. And this elegantly shows the power of the pipeline. Whereas before we had lots of code where we're individually handling every aspect of the triangles, that's now all encapsulated and abstracted away. We just specify the properties that we want for rendering. One of the things I know I'm going to need is my texture, which contains the road sections and building sections. And the nice thing is, the textures are just standard OLC sprites. So I'm going to create a variable called SPR_all, which represents the entire sprite sheet. And in OnUserCreate, the first thing I'm going to do is load up the PNG file that represents that sprite. Now that we've got a sprite loaded, we can use it as a test texture for our cube. All we need to do is specify which texture the pipeline should borrow from. Set texture SPR_all. But we can't render a wireframe with a texture, and in fact, given that most of the time you want to render with textures, the default options are to render using the texture and not wireframe. So this will now do texturing, clipping, and backface culling all by default. Let's just take a quick look. And it looks like a horrible little mess in the middle of the screen. In fact, it's failed utterly and completely, and there is a reason for this. As well as clearing the screen to black each frame, we also need to clear the depth buffer of the 3D system. Unfortunately, this is also very simple to do as well. We're just going to call the clear depth function of the extension. So there we have it. It's a bit small. Let's see if we can zoom in. The reason it's a bit small is the cube is rotating around the origin of the world, 0, 0, 0, and our eye point is 10 units back. So I'm going to change that to -4. There we go. That's better. A rotating cube, always a sign that you're on the right track.
Now I appreciate if you've come to this video without having seen the 3D Graphics Engine series, a lot of this might seem a little bit confusing. Well, it's probably really worth checking out that series before carrying on with this big project series. But hopefully what I've demonstrated to the people that are aware of it is that by encapsulating using this pipeline system, we've now made access to 3D graphics very simple indeed.
Now that we've got the bare minimum of a 3D rendering system, let's start implementing some of our game. At this stage, the game's only going to consist of 2 mesh models. The first is the flat just quad, and the second are the walls facing outwards. We'll use the flat quad to render the ground, the roads and the roofs, and of course the walls render the stories of the buildings. We'll need to populate those meshes with some data. So this is the flat quad, which consists of 2 triangles. And a triangle is made up of 3 points. This is the first point, second point, third point, and then there are 3 texture coordinates. Now you might notice that these are an additional dimension than what's needed, and that's because we have the omega parameters, or W parameters, as part of those vectors. And the 4 outer walls are very similar. They're effectively quads, but rotated 90 degrees around the relevant axes. One thing to note is that the texture coordinates are all quite simple, i.e. they're not going to index my texture sheet at any particular location. Right now it's taking the whole sheet. So I'm actually going to do a little bit of a hack here. Instead of using texture transformations, which we will look at in a future part of this series, I'm going to break up my main sprite into the individual textures. And so alongside the main sprite, I'm going to have a sprite for the ground, a sprite for the roof, a sprite for the first story, so that's the frontage where all the shops are, a sprite for each story's windows, and then the 12 road sprite sections. Also at this point, going to throw in a sprite for the car. We know we're going to need that later. So the easiest way to break up the sprite is to use the draw partial sprite function provided by the Pixel Game Engine and redirect the draw target. So let's take the lowest floor of the building as an example. I know that the size of my sprite in pixels is 32 by 96. This is effectively going to be this part of our sprite. If I tell the Pixel Game Engine to redirect its draw target to that sprite, all subsequent draw calls will be happening to that sprite rather than the screen. So now I can just call the draw partial sprite function, which has been around since the early days of the console game engine. I can specify the target location, which is 0, 0, so the top left of our sprite frontage. The source sprite, which is our entire sprite sheet. I choose the exact coordinates within that sprite sheet and the width and height of the target sprite. And I want to do that for all of the sprite sections. I've deliberately laid out the road sprites lumped together in a 3x4 grid of sprites. So 1, 2, 3, yes we've got some grass here, that's falling into that, 4, 5, 6, 7, 8, 9, 10, 11, 12. This makes it easy to algorithmically break up the road sprites instead of specifying them all individually. I know there's 12 of them, so I'm going to create a little for loop to iterate through 12 different positions. And I've got my road sprite, I'm going to create a new one for each of those locations. One of them's redundant because it contains grass, but it doesn't matter, we'll just never use it. And again, as we've done before, I'm going to use the draw partial sprite routine to populate that sprite with the correct section of road. But the nice thing is I can use integer division to choose that sprite location for us out of the main texture. So I can find the X offset by modulating by the width of each of my sprite tiles. So in this texture, one of these tiles is 96 by 96 pixels. So by modulating by 3 and timesing 96, I can choose the right column across the screen. And conversely, doing an integer division by 3 and timesing by 96, I can choose the correct row.
And I think this is quite important because it shows that how you organise your game assets can actually make your coding a lot simpler.
Once we're done loading all of the main asset textures, I want to set the draw target back to null pointer. If you don't do this, you'll always be drawing to the sprite that was last set as the draw target, and you may end up with a blank screen. And then finally, a quick easy one, I'm just going to load the car sprite too. Let's define our cell as a struct, sCell. And we know that this is going to contain the height value as an integer and a flag to indicate whether it's a road or not. And we're going to want a 2D array of these, so I'm going to specify a map width and a map height variable and a pointer to what will ultimately be an array of cells. And I'll create a default map in onUserCreate. So I'll just find the bottom here, there we go. So my map is going to be 64 wide by 32 high. I'm just going to dynamically allocate that memory. I'll then create two little for loops to iterate over all of the x and y locations within that 2D array. And I want to set all of the heights to 0 and all of the road flags to false. And here is something I've done in probably every video of the One Lone Coder channel. We've got y times map width plus x. That's translating our 2D coordinates into a 1D coordinate for our array. Now it's time to start rendering our map. I'm going to keep the clearing and the clearing of the depth buffer and setting up our camera. And for now, no optimization at all, I'm going to render everything. So I'm going to create 4 integer variables, start x and end x, which is going from 0 to map width, and start y and end y for map height. I'm just going to render everything, even if we can see it or not. Which means, again, I'm going to want 2 for loops that iterate through all of these locations. For each cell that we're going to draw, I'm going to test, is it a road or not? Right now, if it is a road, I'm going to ignore it. If it's not a road, we're drawing some scenery, so let's start with that first. If you remember back to the plan, we know if the height is 0, then we're just drawing a flat grass quad. So let's configure our rendering pipeline to do just this. We've already set up the projection and the view matrices, so the only thing left is the world matrix. Rendering the cell is quite easy because our cells are all at integer locations, and our 2 loops are iterating through integers, so all I need to do is translate this particular cell to its integer offset in world space. I'm going to tell the pipeline that that's the world transform it should use. I'm then going to tell the pipeline that it should use the grass texture. And finally, I'm going to tell the pipeline that its source of its geometry should just be the flat quad. And that's it. So I'm going to get rid of our cube rendering stuff from before. Because I think blue is a slightly more appealing colour, and at the moment I want it to kind of represent water, I'm going to change our clear colour to blue also. So let's take a look and see how this works. Well, we can certainly see a grass texture in the bottom quadrant of the screen. It looks like it's going to 0, 0, 0 in the middle. Excellent. Though I'd like to verify that it's drawing the whole world by including some rudimentary camera control. I'm going to add 3 variables which represent where our camera is going to be. And in onUserUpdate, I'm going to test if particular keys are held down and manipulate the camera accordingly. So the first one will be checking if the W key is held down. So we'll use W, A, S and D to move the camera. OLC, key, W. If that's held down, we're going to change in the Y direction, which is up and down the screen. So camera Y minus equals 2.0, and I'm going to modulate that with f elapsed time. And it's quite important to modulate things with f elapsed time so that they move smoothly even though the frame rate is going to change. So in a similar way, I'm going to implement the other keys. I'm also going to include 2 more so we can change things in the z-axis. We can zoom in and out, z and x. Now that we've got 3 floating point variables that represent where the camera is, we want to update our view matrix. I'm going to set the eye point to be at that camera location. So let's take a look. So I'm pressing the D key and very nice, the grass is moving across the screen. S moving up, and I should be able to zoom out. Let's have a look. And so there we can see all of the cells, all what was it, 64 by 32 being drawn to the screen. And we can zoom right in and see the individual pixels of the grass texture. Very nice, I'm pleased with that. I think at this point it would be fun to add the car to the scene. I'm not going to create additional geometry to do this. I'm going to use our flat textured quad. But there are some transforms I'm going to need to do to this. Our quad is currently 1 unit in size. It occupies an entire cell in our city. Clearly the car shouldn't occupy the entire cell. And I also want the car to be able to rotate. But right now, if I rotated this quad, it's going to rotate around its 0, 0 position. It's going to look a bit strange. I want it to rotate around the middle. And finally, the car is actually a rectangle. It's not a square. So we'll need to change the shape of this quad. And we'll do all of this with matrix transforms. So the first transform I want to do is to offset the quad so that its origin is in the middle. So I want to offset by a OX and an OY value. In this case, that's quite easy. It's half in each axis. Now the quad is centered around the origin, I can rotate and scale it. So I'll scale it first to suit the size of the car relative to the rest of the world. And through a little bit of experimentation, I've determined that the car should be scaled by 0.4 and 0.2, and that of course will change this square into a rectangle. So after it's been scaled, it'll look something like this. After I've scaled, I'm going to rotate the quad to suit the direction of the car. Now currently, after all of this, the car is still at 0, 0 in the world, so I then need to translate it into the world, into its realistic position. So translate into world. So there's a bunch of matrix transformations required here to put the car in the right size, the right orientation, in the right place in the world. I'm going to add some additional variables to handle the car. The first variable is going to be a floating point value that represents the angle of the car. And the second value is going to be the speed the car can move at. Now we saw in the plan that we might want to externalize that later on, but for now I'm going to hard code it in. I'm then going to want 2 additional 3D vectors that represent the velocity and the position of the car. Now we've done velocity and position many times on this channel, and it's no different in 3D than it is in 2D. Using the arrow keys, I'm going to detect if they're held down, and if they are, I'm going to adjust the angle of the car accordingly. I now want to break down that angle into a normalized velocity vector to indicate which direction the car should move. And whereas traditionally I would break out the sines and cosines to do this, well, we've now got an engine that can do rotation transforms for us. So I'm going to create a unit vector, and I'm going to take a rotation matrix in the z-axis, so this is looking down from above, and rotate that unit vector by the car angle. And we'll take the product of that matrix and the vector and place it into our car velocity vector. Now that's currently normalized. To drive the car, we're going to respond to the up arrow being pressed. That'll move the car forwards. So let's put in an event handler to deal with that. And since our velocity vector is normalized, I'm going to multiply it by car speed and modulate it by f elapsed time. We're effectively integrating our velocity to give us our position. I've done that for the x-axis, and I'll need to do exactly the same for the y-axis. And the important thing to note here is that because car vel is normal, we're effectively changing the magnitude of it by multiplying by this scalar car speed. So this is a very primitive way of handling a car. It's not realistic car physics at all. We can rotate the car on the spot, and it has no acceleration or deceleration. We'll look at that sort of thing in a later video of this series. I want to ensure that the car is always kind of visible. So I'm going to draw the car after I've drawn the scenery. And I'm just going to go through the transforms I've just been through in the slides. The first thing is to offset the quad by half. So now the origin is in the middle of the quad. And then going to scale the quad to make it into a rectangle the size of the car that would seem realistic in the world that we're creating. The order that we multiply matrices in is important. So I'm going to combine the translation and the scale matrix into what is now going to be the car's world matrix. Next, I'm going to create a rotation matrix so the car is facing in the right angle, and we can use the car angle variable that we've already got. We don't need to reverse engineer the velocity vector. And I'm going to multiply that rotation matrix into the current world matrix for the car. Finally, we want to translate the car into its real world position. So I'm just going to translate it by the car's position X and Y, but I'm also going to give it a little tiny bit of elevation. Oh, just spotted a little typo there. And this raises it slightly above the ground plane. This means we won't get any depth buffer conflicts. But it also won't look strange either. It's so close to the ground plane that it'll look like it is on the ground. So we can combine that translation matrix into the current world matrix. So you can see there's quite a few transformations for the car, but they make sense. Now we'll tell our pipeline to draw the car. Well, since we've just calculated the transform, let's apply that to the pipeline. And we're going to be using the car texture. And here's a little bit of a Pixel Game Engine peculiarity. The car texture I'm using contains alpha components. It's got transparency. So we don't want to draw those particular pixels. Now this has nothing to do with 3D graphics, it has everything to do with the Pixel Game Engine itself. So I want to enable for this particular draw call alpha blending. Once I've enabled the alpha blending, I'm going to tell the pipeline to actually render the flat quad using its world transform. So we're not adjusting the original geometry, we're just transforming it as we've just seen with the matrices. And because alpha blending can be a little bit expensive, we don't want to do it all the time, we'll tell the Pixel Game Engine to go back to rendering normal, i.e. it doesn't assume there is any transparency to the pixels and just does it very quickly. So let's take a little look at our little car. Well, there's certainly a yellow blob on the middle of the screen. Let me zoom in a little bit. Oh, that's zooming out, zooming in. There we go. So we can see the car sprite. Very nice. And it is alpha blended. We don't see sort of any white sprite boundaries around the car. It's also rectangular, which means our scaling has worked very nicely. So the left and right arrow keys should rotate the car. Very good. And the forward key should move the car along its rotated vector. Oh, there we go. It does. Let me zoom out just a little bit and we can drive the car around. I mean, it doesn't handle anything like a car that I've ever seen before, but it's it's a good enough approximation at this stage in the big project. The only downside is I've got to now manipulate the camera and control the car simultaneously. I just don't have enough fingers. So what I'm going to do is attach the camera, going the wrong way, attach the camera to the car. And this is very simple. Where we set our eye point for the camera, I'm just going to set the X and Y camera values to our corresponding car position X and Y values. Let's take a look. So now I can't control the camera anymore with W, A, S and D, but the camera follows the car. Very nice.
I think now it's time to start thinking about placing the roads.
To begin with, I'm going to do this incredibly crudely. Wherever the car is, if the user presses the R key, I'm going to toggle the road flag for that particular cell. So first, let's be sensitive to the R key being pressed. And I'll truncate the car's floating point position to integer position so we can index into the map. I'll do this for X and Y. And this is a really good advantage to having a cell-based city, is we can easily work out where we are. And this is working in exactly the same way as the code-it-yourself platform game. So since that we know where we are, we can simply toggle the flag for that location. Y times n map width, again, plus x, dot b road is equal to not all of that. So it depends which cell the car is in. If we press the R key, it's going to toggle whether it's a road or not. But we don't render road yet, so we need to sort this out. Looking at the complete sprite sheet, we can see we've got 11 different types of road section. As I'm rendering the roads, if the flag is set to true, that's where I'm going to determine which particular road section I should draw. And I'm not going to do anything too clever to determine this, I'm just going to test it explicitly. So we'll start off by assuming that the road value is 0. Now I'm going to be doing a lot of indexing into and out of the array, and I think the code will get a bit unwieldy if I've got y times nmap width plus x all over the place all the time. So I'm going to create a little auto lambda function, r. And this is going to take some offsets, int I and int j. And what I want it to return is the state of the road flag for a given cell relative to the cell that I'm currently trying to render in our for loops using the x and y coordinates. So I'm going to look at the map array, and I want to check for the current location that we're rendering, y, but plus the offset j. And of course that's times n map width. And I want to do the same for x, but this time plus the offset I. So this will allow me to interrogate the neighbours of the cell that's currently being rendered. And I want to return whether that is road or not. So, labelling our roads, the top left one up here is 0. And then 1, 2. Then we go down to the next row of roads, 3, 4, 5. So road 0 is a vertical strip. That means this one is only applicable if the road above it is road and the road below it is road and its left and right neighbours are not road. So I'm going to test for that explicitly. So if the road above me, so my x offset is 0 but the one above me is -1 in the y. If that is road and the road below me, 0 again, I'll put a +1 in. Of course the plus isn't necessary, but it helps visualise what's going on. So if the road above me and the road below me is road, and this is also important, we must test for our left and right neighbours. The roads to the left of me, -1 in the x-axis, and not road +1 in the x-axis. So if my left and right neighbours are not road, then I want to choose the vertical section. So if all of that is true, then I know that I want the vertical strip of road. In a similar but kind of opposite way, I can check for the horizontal strip, which has a road ID of 1. Here we can see we've got no vertical components, but we've got both horizontal components. That's the first top row of our sprite sheet. The next row down, we're looking for a corner section, a T-junction and a corner section. So the first corner section is true if the one above me doesn't exist, but the one below me does. The one to the left of me doesn't exist, but the one to the right does. That's clearly a corner. The next sprite ID along was a T-junction, going horizontal but with a southern opening. So there is no northern neighbour component, but all of the others must exist. And I'll keep going on like this until I've covered all possible road types. So now that I know which road sprite to set as my texture for the pipeline, I can just go ahead and do that. The world transformation for a section of road is exactly the same as drawing a section of grass, so I'm just going to cut and paste that. And in fact, so is the rendering. That's all the same, because it's just simply flat. So let's take a look and see if that's working. We just zoom in, and I'm going to press the R key to toggle the cell that's underneath the car. There we go, it's turned into a road, a vertical section. Well, it's got no information to actually make any sensible judgment, but I'll go to the one next to it. Still not quite right, but if I go here, and here, and here, and we keep going, and if I just test the toggle nature, yes, so I can disable and enable the roads, and I'm going to turn down here, we can see it's chosen the correct corner for us. So let's try and make a loop. Very nice. There we go. So we've got a nice loop of road. I'm going to choose this middle cell now. Oh, well, I can't choose a middle cell, it's only too high. So let's go over here and try a bit of a T-junction. Yep, there we go. Very nice, so that's put in okay. So down here, this should also now become a bit of a dead end, which we shouldn't really allow, and we can see it's chosen the crossroad. So let's loop this back round. Go up here, there we go. So it looks like as long as we maintain loops for our roads, it can choose the junction sprites accordingly, which is very nice. That makes editing roads much simpler indeed, particularly when you consider how large the city can be. At this point you may notice that there's a few sampling glitches going on, and we'll look at that in a future video. Some of the eagle-eyed viewers amongst you may have already noticed the term MIP in this code, and yes, we'll be considering that in a future episode. But for now, I'm just not going to worry about it. It's rendering the roads. Good. Now let's implement the rendering of the rest of the scenery. Well, the first thing, if you remember, is if we had a less than 0 condition. We don't want to render anything at all. So I'm just going to throw that in. Later on, we will want to render something for this condition. I want to render water, but I'm going to leave that again for a later episode. That's a bit more of a cosmetic effect. But for now, if it's less than 0, we don't want to do anything at all. And this leaves the final state, is that if it is greater than 0, we want to draw the building.
Now, some of you that have familiarity with 3D graphics may be thinking it's quite wasteful to draw each story as a unique set of polygons. Why don't we just take a cube model and scale it to the height of the building? And we will, at some point, we'll look at how we can do that, because at some point I also want to introduce texture transforms, which are also a necessary component of being able to do that. If we were to just scale the building right now, the texture would also stretch, and we need some way of compensating for that. I'm also not going to look into making sure that we can render walls that we can see. That's going to be coming up in the next part of this series. So if we've got two buildings the same height which are next to each other, they're going to both render the walls that will be touching each other. And of course there's no need to do this. But right now I just want to make it work, and then I'll make it work well.
So depending on the height of each building, each story of the building is going to be a repeat of the outer wall's mesh, but we're going to have to translate it in height. And given that I'm drawing each story as a separate mesh, we're going to have to do multiple renders depending on the height of the building. I'm going to start by having a for loop that iterates through each story of the building. And I'll want to create a transformation world matrix for that particular mesh. Here I use a translation matrix as normal. We can see the X and Y components offset the mesh into the correct world location. But we need to think a little bit differently about the height. The ground is at 0, 0, 0, and the camera is currently at -10 in the z-axis. So things get more negative as they come towards the viewer. So here you can see I'm multiplying by -1 to compensate for that. The mesh is also defined as being 0, 0, 0 at the top and 1, 1, 1 at the bottom, which means if we were to just draw it directly, the first story would be level with the ground and therefore behind it. So I'm going to offset the height by 1. Finally, I'm going to scale the z-axis displacement by 0.2, because in our world each story is 0.2 of a unit cube high. Once we know where the story is in world space, we need to choose the appropriate texture. If it's on the ground floor, I want it to use the frontage. But if it's off the ground floor, I want it to use the windows. So I'm just going to use the ternary operator to quickly choose which sprite it should. And finally, render the walls. In a very similar way, I want to draw the roof for the building. Now this is just the flat quad that we've been using before, but I need to change its Z displacement. And in fact, I'm just going to use the H value that we're left with at the end of this loop. Now that we can potentially render buildings, we need to be able to specify where the buildings are in the map. I'm going to use the T key to increase the height of a particular cell, and I'm going to do that in exactly the same way that I have for specifying the roads, except this time it's just going to be n height plus plus. And I'm going to use the E key to decrease the height of a particular cell. So that plus plus becomes a minus minus. So let's zoom in and press the T key. And we get what looks like the roof of a building. Zoom in a little bit more. Can't see the sides of the building until we start driving around. So we've got a building there. So let's press T twice now. And we can certainly see the building is growing, and it's rendered very nicely too. So let's give it a neighbouring building. Now don't forget, I'm not doing any optimization, so there's loads of polygons there being drawn that we can't see. Let's add another one. Let's add one over here, and one here, and one here. And in between these, I'm going to set some road. Very nice, it's starting to feel right. And I can drive into a building, of course, normally you wouldn't be able to, and if I press the E key, we're decreasing the height, and if I set it below 0, the cell doesn't get rendered at all. In fact, we can have very, very tall buildings indeed. Let's see how good we can go. Pressing the key a lot. That's very nice, so we can have like a massive skyscraper in our city.
Using the car as a selection mechanism to determine which cell we want to operate on is fun, but not very practical. I'd rather use the mouse. But this adds some complications. In a 2D game, working out where the mouse is relative to the game world is quite simple. But in a 3D game, it isn't quite as simple, because we can zoom in and out. and so this will obviously change which cells lie underneath the cursor. So let's have a quick look at how we can use the mouse through the projection and view matrix to determine whereabouts on the ground plane the mouse is above.
Now, because this, for me, becomes quite tricky to draw, I'm going to assume we're looking at things side on. So this is the monitor screen side on, and therefore here is the player's eye. The purpose of the projection matrix was to translate the world into a 2D image, using some sort of function that looks like this. So we can envisage our game's ground plane existing down here. The problem we've got is the relationship between the mouse cursor, so let me just put a little arrow here to represent the mouse cursor, is not directly relative to what we see in the world. It has to also follow this projection. So if the mouse cursor is there on the screen, it's not here in the world. Instead, it follows a projection. And this gets more complicated because as we zoom in and out on the world, of course if the ground plane moves up, this is a different location to this. Now this is so far assumed that our world is completely centered around 0. And of course it isn't, because we have a camera, and that camera also influences where our mouse positions are. So to solve this conundrum, what we want to do is create a mouse picking ray. And so we're going to assume that the origin of this ray is here, and that the direction of this ray is using the only information we've got at hand, which is the screen coordinates. Once we know the direction of this ray, we can then project the ray into the world and see where that ray, or that line, intersects with our ground plane. And we covered in quite some detail line-plane intersections as part of the 3D Engine series. And so I'm going to reuse the line-plane intersection functions to work out where my mouse is on this ground plane. But first, how do we work out the properties of this ray? Well, to the 3D Engine, if you recall, one side of the screen is -1 and the other side of the screen is +1. So the first thing I want to do is translate the mouse's screen coordinates into normalized coordinates defined by our viewport. And there's one additional hiccup to all of this, is that we must remember our screens are not square. Typically they have an aspect ratio. So if we assume one of these sides is -1 to +1, the opposing axis is probably going to be -1 point something something, let's say 1.2, to +1.2. And we can get that information about how to do this very simple transform from our projection matrix. Therefore, since we know this location, let's assume it's 0, 0, 0 in 3D, we can easily calculate this location. We've then got a direction for our ray. Ultimately, the end goal here is to work out which integer cells is our mouse cursor above. I'm also going to add in a projection matrix. Now you might think, oh, we've already calculated one of those. Correct. And here it is. We set it up as part of our rendering pipeline. However, this time I want one that's explicit. So it's exactly the same parameters as the ones we've given to the rendering pipeline. It all gets calculated once, so there's no performance hit in doing this, but now I've got a projection matrix where I can access the individual elements. Naturally, we can only work out where the mouse is once we've established where the camera is in the scene. So we'll start putting in our mouse detection code below where we set the camera for the pipeline. I know that my mouse's origin is going to start at 0, 0, 0. And as I've just described in the slides, we can calculate the ray quite easily by normalizing the screen coordinates and compensating for the aspect ratio. I can take the individual elements out of the projection matrix we've just calculated for this. Another way to think about this is we're effectively using the inverse of the projection matrix multiplied by the mouse coordinates. And that's actually quite a sensible way to think about solving this problem, i.e. we take a triangle, we multiply it by a view matrix, and then we multiply it by a projection matrix to give us a 2D coordinate of where that triangle is in the 3D world. So it makes sense that if we take a 2D coordinate and multiply it by the inverse of the projection matrix and multiply that by the inverse of the view matrix, we'll get some information related to the 3D world. Now we've already specified a view matrix for our camera, and if you remember from the 3D series, the view matrix is otherwise known as a look at matrix, and the look at matrix was the inverse of the point at matrix. So I'm going to create a point at matrix using our camera properties, the eye, the target and the up direction. So this is technically the inverse of the view matrix, but we've not had to calculate the complex inverse calculations. Now that I have the mouse's origin and the mouse ray direction, I want to transform them by this point at matrix, which will offset them into the correct location in the world. Now this ray is currently around the origin 0, 0, 0, so I need to offset the ray to be around the transformed origin, around the actual place in the world. So now I've got all of the information I need to do my line plane intersection. I've got the start of my line, which is effectively mouse origin, and I've got the end of my line, which is now vec mouse dir. So I've got a line segment. I can now see if that intersects with the plane. Defining the plane is very simple. We're going to use point and normal notation to do this. Again, check back on the 3D video series. And a point on the plane is easy to calculate because the plane is a ground plane. It is at 0, so we can choose 0, 0, 0. We know that that's a point that exists on that plane. And the normal to the plane is in the positive z direction. And I'm just going to call directly the intersect plane function from the math library. And that returns a single point. Whereabouts on that plane did that line segment intersect? So this has given us our mouse coordinates in the 3D world along the ground plane. A very useful thing.
Whilst I was developing this, it became quite frustrating to do everything on a single cell by cell basis. And so I thought it was necessary to add a tool to select multiple cells and affect them all at once. So to do this, I'm going to use something that we haven't seen on this channel before. I'm going to use an unordered set.
If you've not encountered an unordered set before, they're a very interesting container. But they're quite complex, so I'm not going to go into the detail of how it works right now. There's a lot already going on in this video. But they're interesting from a computer science perspective. They behave like pretty much other containers, vectors, lists, etc. And the most critical feature, the part that I'm interested in right now, is they don't permit duplicates. So you can keep throwing the same thing at it, it will only store one instance of it. And no duplicates is exactly what we want. So I'm going to add an unordered set of cell pointers called setSelectedCells. And once we've worked out where the mouse is in 3D, we can cache these in our nmouseWorldX and nmouseWorldY variables. When the user presses the left mouse button and drags it, I want it to add cells to the set. So I'm going to check for if getMouse0, which is the left mouse button. If that's held, which I guess indicates it's been pressed as well, I'm going to add to the set of selected cells the current cell at that location, and use the InPlace function to do this. Now I want to add a pointer to the cell at that location. So if the user left clicks, we add cells, and I'm also going to add, if they right click, which is ID 1, we're going to clear the set. And it's quite important that I indicate to the user which cells they've currently selected. And so after I've drawn the scenery, but before I draw the car, I'm going to iterate through the set container and draw it in wireframe to indicate that that cell at ground level has been selected. But I've got a little bit of a problem. What world transform do I use to do this? All I know is which cells are selected, I don't know where they are. So I'm going to have to add something to the original cell structure. I'm going to add two more variables, int nWorldX and nWorldY. And in the loop where we create the default world, I'm also going to populate those values with the X and Y locations. Now this may seem a little bit redundant, but it does make life a lot easier if the cells know where they are in the world. So now I can establish a world transform very easily. I'll just set it to the pipeline, and I'm going to render our flat quad as wireframe. So let's just see if this is working. If I click, we can see a cell has become highlighted, and as I drag, I can select more and more of them. And I'm fairly reassured I'm not going to be getting any duplicates whilst I'm doing this. And if I right click, they all get unselected. If I move the car, I can select different cells in the world. And I can zoom out, and I can select quite a few different cells. Excellent. So now I'll modify our three routines for altering the contents of the cells. But the first thing I'm going to do is just to check to make sure that our mouse coordinate exists within the bounds of the array. We don't want any sort of out of bounds errors. So I'm just going to do that by wrapping all of this in a big if block that checks against the size of the map in both X and Y. Now, if the R key is pressed, we're toggling the road. And I quite like the idea of being able to toggle the road without needing to select the cell. So if I hover over a cell, don't click anything with the mouse but press the R button, I want that one cell to become road. So I'm going to test if the set is empty or not. If the cell is not empty, i.e. we've got some selected cells inside it, then I'm going to need to do something different. But if the cell is empty, then I just want to toggle this particular cell we're hovering over directly. But if we do have some cells, I'm going to use a little auto for loop to iterate through all of the cells and toggle the road flag. We're also not using the car position anymore, so I'm going to get rid of that, and I need to change the X and Y values down here to represent our mouse coordinates. So this gives us a multi-angled approach to editing cells. I'm going to do exactly the same for the T and E keys, raising and lowering the height of the building. I'm going to select some cells, all of you, press the R key, become a road. Excellent. Clear the selection. So let's draw a slightly more complicated network, which is much easier to do now than driving the car around like it was before. Press the R key, they all become roads too, and the junctions and everything are working out as they should do. Let's say I want a building in this one, I want it to be 4 units high, so I press the T key 4 times, 1, 2, 3, 4, and this one I want them to be, I'll have a mixture, so you lot, and you and you can be taller. Now let's zoom in and just take a look at what's going on, see if it looks okay down on the street level. And so that's quite a nice, quick and rapid way to edit the scene. There is one small thing, and that is I feel the performance is a little bit clunky. And that's because we're drawing everything all the time. And you might think, oh no, we're going to go into a whole load more maths to try and work out what's going on here, what can we see? And actually there's a very quick fix for this. Now we've got our mouse coordinate.
We now have the ability to use our mouse to convert from screen coordinates to some coordinate on the ground plane in the game. Well, of course, that mouse coordinate can change between anywhere on the screen. Fine. If we took the top left value of the screen, which is 0, 0, and the bottom right value of the screen, which is screen width and screen height, we could also calculate rays that represent the extent of the viewable universe. And this means we can draw cells between those extents, so we're only drawing cells that we can see. And this is a fantastic optimization.
And some of you may be wondering, why on earth did he create the start x and end x variables in the first place? They're just part of this loop. Well, that's because I have the ability to see into the future. And so I'm going to borrow exactly the code we used for the mouse coordinates. Now we're done with mouse coordinates by the time we've selected cells, so I can reuse them. And I'm going to hard code in this case, our mouse coordinate is -1 and -1, so that's our top left. And I can work out the bottom right with +1 and +1. So it's another set of matrix multiplications and plane intersections, but it'll give me two variables, the world's top left and the world's bottom right. So I need to add those to my program. So I now know where to start and end in both axes of my 2D array. But because we can pan the camera around and zoom in and zoom out, I want to clamp this to make sure that we don't try and sample the array out of bounds. So I'm going to replace these 4 lines of code with 4 similar lines of code, but this time I'm using max and min to clamp against the array boundaries to make sure that we're not selecting cells outside the array. And I'm also going to draw one cell beyond the extent that we can see. We get a nice smooth screen, and I can already see the frame rate has gone up 5-fold. And so there you have it, a simple engine with editing capabilities that will form the foundation for our top-down city-based car crime game.
Even though it's early days yet, I'm quite excited about this project. I think there's a lot of potential to talk about many interesting algorithms. In the next part of this series, I'll be implementing collision detection, but before then I'm going to release a video about how the collision detection works in a more general purpose way. Anyway, I'm also going to start releasing the source code straight away, so the source code is already available in GitHub for this. If you've enjoyed this video, give me a big thumbs up please, have a think about subscribing, come and have a chat on the Discord, and I'll see you next time. Take care.